Okay, now we're going to use a technique called implicit differentiation. And it is when you have these special types of functions that using the traditional method may not work. So here's the rule. Every time you take the derivative, only the derivative, if we're doing it in terms of y, the only time when you're taking the derivative of y, you're going to tack on dy dx. So for example, we're going to take the derivative of each of these. The derivative of x, the first, is just 1. The derivative of 2y cubed is 3 times 2 is 6, is 6y squared, and now you take the derivative of y, so dy dx. The derivative of constant of 3 is 0, so we don't have to write anything. Now, what we want to do is we want to get this all by itself. So we're going to divide both sides by that attached multiplied 6y squared. So I'm going to write it on this side because that's what our brain's like. dy dx is 1 over 6y squared. All right, let's do one a little bit more complex. This one tells us to find, this is a lot more complex. This one tells us to find the second derivative, and note so the raised 2, the x1 of 2 goes above the d, but down below the raised 2, so that's the notation that you would need to write. So we first have to find the first derivative. So we're going to take the derivative of x cubed, that's 3x squared, plus the derivative of 4y squared is 8y, but we're using implicit, so we tack on dy dx. The derivative of a constant is 0. Well, we want to get this by itself, so using our algebra skills, we're going to subtract 3x squared. So what we have is 8y dy dx is equal to negative 3x squared. And now, to get the dy dx by itself, we can just divide both sides by 8y. So this is what we have. Our dy dx is equal to negative 3x squared over 8y. This is very important because when we use implicit differentiation for the second derivative, we're going to have a dy dx, and then we're going to take this dy dx and on the next problem, and we will substitute it, and we will write in, instead of dy dx, negative 3x squared over 8y. All right, so now we're starting off with our function is I'm going to leave it the way I had it. Our first derivative looks like this. Now we need to find the second derivative. So d2y over dx squared, we have a quotient rule. So here's your g. We'll do this in a different color. Here's your g, here's your f. So f prime is negative 6x, because I'm going to put the negative sign with the 3. And then g prime is 8, but because there's a y, it would be 8 dy dx, because we're using implicit. All right, so let's do the quotient rule. The quotient rule says g times f prime minus f times g prime all over g squared. So we're going to take g, multiply it by f prime. We're going to subtract f well, subtract a negative, that's going to become adding, times the derivative of g, which is 8 dy dx, and then all of that will be over g squared. But where this dy dx was, we're going to end up substituting negative 3x squared over 8y, and I'll do that with the next step. So now we have d2y, or d squared y is the proper way to say that, over dx squared is equal, so 8y times negative 6x is negative 48xy. And we already said that this was subtract and negative, so that becomes plus. Now we've got 3x squared times 8, that's 24x squared, but now we're going to multiply it by dy dx, and dy dx is negative 3x squared over 8y. And then all of that will be over 8y squared is 64y squared. Look at what we have. We have this whole thing right here has a denominator of 8y. Let's see if anything can cancel. Oh, the 24 and 8, so that just leaves a y. This becomes a 3. But now we have to multiply top and bottom here by a y. Well, look at what we have. I'm going to multiply this top and bottom by 64y squared. So now, when we simplify everything, I'm going to bring this down a little bit more. So 60y squared times y, in the denominator, we're going to have 64y cubed. So that takes care of everything in the denominator. So now we can just focus on what's left in the numerator. So we have negative 48x, y times y, so negative 48x, y squared. We have a 3x squared times negative 3x squared, so that's negative 9x to the fourth. Ta-da! That's it. All right, and then I'll pause for just a second. So you find the first derivative and use that to substitute into the second derivative. And that's what we did right there. So this thing right here, where it was dy dx, that's where we substituted it. Okay, one last one. When there are more than one terms of x and y. So there's a lot going on here. There are two different y's. All right, so on the left side, we have a constant. So right away, we can say that is equal to 0. The derivative of 5x cubed, 3 times 5, so that's 15. 3 subtract 1 is x squared. 5y squared, 2 times 5 is 10. Y to the first, but tack on dy dx. And then 3 times 4, that's 12y squared. Tack on dy dx. Now we're going to want to get the dy dx terms by themselves, so we'll subtract that 15x squared from both sides. All right, and now these both share a dy dx, so I'm going to factor out a dy dx, and when I factor it out from here, we're left with 10y. I factor out here, we're left with 12y squared. And now, to get dy dx by itself, I just divide 10y plus 12y squared, both sides. And then I'm going to write the dy dx on this side. So we've got a negative sign. I'll put that in front of the fraction. So I have negative 15x squared over 10y plus 12y squared. It doesn't look like they share any fact. So in the denominator, these share a y, they share a y. But if I factor out a y, it doesn't cancel, so I'm not going to worry about factoring out a y. 15, 10, and 12, all three of them don't share a factor. 15 and 12 share factors, 10 and 15 share factors, but all three of them together do not share factors. So this right here would be the final answer. Now, if it can simplify, if that would have been a 16x squared, then you could have divided everything, each part by 2. All right, that's it for implicit differentiation.